Okay, yeah, sorry. I think we're good now. Sorry about that.
Okay. So this here is the first kind of external device which I was using, and I'm still using. USB-C on both sides, around 6,000 yen, so something like $50 or $60. And yeah, downside, well, the good thing here is one sees the voltage and the amperes. The bad thing is you have the display, but ideally I wanted in the computer digitally to see the consumption of the external meter. This device doesn't provide it. So I did a second attempt with this device here, and I knew beforehand. Well, the previous device was supported somehow on Linux, I think. For this here, the version 3, there's just a Windows driver. Yeah, nonetheless, I got the device and tried the Python library for the previous device, but yeah, turned out this device here is talking completely different stuff than the previous one. I did also not bother into installing Windows into a KVM guest and then just to read the communication and just to somehow digitally see what the display here is saying. Yeah, anyway, after I got these two, so at least the first one here, the second one, so both of them can show me externally the consumption. Actually, the techie here is smaller and is actually, yeah, more convenient. The second one here turned out to not provide me actually to not let through enough power to properly supply the ThinkPads I was measuring with. So this device here, it's meant for people to buy external batteries like you would use for extending the lifetime of the usage time of your mobile phone. And for measuring this kind of stuff, this device here is good, just not for computers. Anyway, so externally, I still use this Techie for verification. But anyway, yeah, after getting these external ones, I found out the internal stuff or the sensors I afterwards discovered are actually so good that I no longer use the external ones. So what is it I'm using internally? I will introduce two basic technologies to tell something about energy consumption. And on base of this, you can conclude then on consumption of single components. Here, so the basic two technologies, they are available to everybody who can just read a sys file system. Can you guys read this? Is this terminal big enough? Yeah. Is this readable?
Yeah, it's good size.
Okay. So the first of the two technologies is abstracted via sys file system and is called RAPL. So despite me writing a software to conveniently access this, everybody who is just able to traverse the file systems can read this basically with a shell script. And despite the name Intel in it, Intel started to do this interface from the kernel to user land to provide this data. But since 5.x kernels, also AMD, reasonably current AMD CPUs are exporting the same interface. What is it giving us? We get Rappel does more, but what I'm using is to see how much power is consumed by the CPU, by the GPU, if it is on board, like for the ThinkPad, and the memory. So we get this virtual file system here under /sysfs. We get subdirectories, and we get, for example, files like this. So this is a file handed over, a value handed over via this file from the kernel to us. And as you see here on subsequent calls, it's a counter which is increasing. We are mostly after the change between two invocations of the counter. So yeah, basically every sane person reading this will probably want to use the software on top to conveniently access this. Yeah, so REPL is providing CPU, GPU, and memory consumption via these counters. That's the first of the two technologies. And let me also directly step to the second one, which is the battery. So when the system is running on battery, there is no external power used. So as long as we can add this data from our battery, we can also understand how quickly our battery is discharging. And with this, we can compute how much power we are consuming. And that's actually quite accurate. It's, of course, just available on systems with a battery, but it's quite accurate. So I don't want to read these manually, so I wrote a piece of code to conveniently read these. So first part of this introduction here of the presentation is a bit about the software. And the second one, what I did read, what I did find out, or what I was interested in. The software is hooking into Performance Copilot, which is a suite to basically capture and record for later reference and illustrate graphically metrics, something like the system load or how much traffic you have on your network interface, things like this. These are metrics. And my software piece called PMDA Denki is hooking into the software together with PCP, then providing conveniently current consumption, current CPU, current memory, GPU consumption, and then the reading from the battery, how much is according to the battery discharge, how much are we according to that reading currently consuming. Yeah, what's this strange name? I guess the second part I need to explain to no one here, because this is just because I live in Japan and Denki is just the natural term to associate with energy. The first term is from the PCP world and means Performance Metrics Domain Agent, and it means, well, basically plugin to do to be responsible for a certain area. In PCP, we have domain agents then for XFS metrics and for Linux metrics, something like power and memory load and things like this. Yeah. 2 years ago, I was rewriting the domain agent which is responsible for reading and showing temperature. So yeah, in these typical ThinkPads, which I use since many years, we have like 5 or 10 temperature sensors. So actually, after writing that software and before researching about which sensors we could use to directly read the electrical power consumption, I was looking at the graphs of the temperature readings inside the system, and I was thinking, actually, we are just converting power, electrical power, into heat. So actually, just from looking at the sensor readings, at how much the system is heating up, we should also be able to conclude on how much power we consume. Yeah, luckily, or well, maybe not, maybe it would have been interesting. I did not get into that research, but actually, this still looks reasonable. And in fact, I did, of course, afterwards, I found about REPL, one of the two technologies I'm using. And people on the internet have, of course, done real studies on how good the measurements from REPL are. And they also did fall back into actually comparing this with temperature readings. Anyway, if someone wants to try this, it's a great approach, great idea. One of the things is one would like to have the temperature which is consumed by the system. So a ThinkPad under full load being in a fridge will have different, will heat up differently from being in the current 30 degrees, 80% humidity air of the Tokyo environment. So this would be to be considered, and unfortunately the air which is consumed is not directly measured by a sensor. Anyway, what is it I'm doing software-wise? PMD8 Denki is using the two sources I was mentioning and practically providing various metrics. The 5 metrics I have here on the bottom of this screen. Here, this box should be the one system, the Linux system, for example, a ThinkPad. To the left, we see the power coming in. We have an external power meter, which I use not anymore, actually. Then we have here this one wire coming in. We have here this one sensor, which is DenkiBud power_no. This is delivering us the current consumption, and it's updated something like once per second. And we see here consumers hooked up to the right, and to the top we see the internal battery hooked up. So this also hints at this one sensor. Also, if the power supply is connected to the system and we are charging, because previously, well, the battery is not completely charged, then it will charge. And also at this time, we can see on this value, this metric here, the rate at which the system, well, the battery is charged, plus what we are consuming. Yeah, we have here energy now rate, which is painted a bit more into the direction of the internal battery, which is hinting at, yeah, when we are normally just consuming power, then this sensor doesn't show us anything useful. And basically, we have a value which is telling us the current rate of how much energy we have in the battery. And the energy now rate is basically just looking at this charge level at 2 different times and then computing the energy now rate. More or less the same as power now for most usages. To the right, we have more or less the consumers, the eaters. To the to the extreme right here, we have the CPU, the internal GPU, and the DRAM, and these are having dedicated metrics which are part of REPL, and then this package -0 metric is also provided by REPL. So these 4 values here, they are basically available on all recent CPU, being them from Intel and being them from AMD. Unfortunately, not ARM. So these 3 metrics, as the picture tries to show, is then the dedicated consumption of my CPUs, of my internal GPU, of my RAM, and the package -0 is summing up these 3 for us. And then we have a big unknown X. Well, sensor-wise, a big unknown, which is fan, display, NVMe, USB ports. And these are, well, they are consuming when we are running on battery, but they are not dedicatedly measured. Motherboard manufacturers could do this, but basically not enough people are interested. You could put sensors and they would be dirt cheap probably everywhere, like we have temperature sensors on the board. Apparently not enough people are asking about them. Anyway, I was successful to learn more about the consumption also of these 3. Yes, the basic description. The Denki term is clear to everybody here. Yes, this is just taking already a bit of my software measurements. This is a nice graph here. So I was saying I'm hooking my PMDA Denki is hooked into PCP framework, which means I get all kinds of stuff for free. I get logging of historical data. So what was the consumption yesterday or yesterday night or something? Could be recorded there. And I get also all kinds of interfaces to graphical visualization. And PCP is also nicely interfacing with the Redis database and Grafana on the top for visualization. That's where this graph here is coming from. And what do we see here? On the top, we see the pure stuff, the pure REPL readings. So basically, every plane, unfortunately not the nice ARM system from Jim, but the energy wasters from Intel and AMD will have the REPL readings we see here on the top. So to the left, we see basically an idle system until 5 o'clock here. And then I think an online conference was started. And then we see the green stuff here is all of the REPL readings. So it includes the other 3 here. So yeah, the REPL area was around 4 to 5 watt consuming. And then here at 5:45, I was disconnecting the battery. Wait. Battery. No, right. So also at 5, I was not only starting the conference, I was also shortly before 5, I was disconnecting the power supply. So starting from then, I was running on a battery, and this enabled me to get Energy Now and Power Now readings. And again, Power Now is basically, I think it's in the firmware, not from a driver, updated once a second and giving us an estimation of what we are consuming. Also based on looking at the charge levels of the battery. And Energy Now is calculation by me inside of the PMDA Denki code, which is once per minute looking at the current charge level of the battery and from that computing. So we see here these two values actually being more or less the same, which is a good thing. And we see, yeah, and then the conference was stopping. We see no longer CPU and GPU and everything consuming. These levels here are at the same level as before 5 o'clock. And then we start charging. And we see that power now, I have no influence on that one. I'm not manipulating that one. This one is then going up and showing us we are consuming basically 20 watt from the plug in the wall. And we see here also that just looking at the charge level of the battery, which this is going up, of course, and this is what we are seeing here also with the with energy now. And we also see that towards full charging, the level of chargement or the speed of charging is going slower, and this is for preserving the battery life actually. So yeah, a description of this, what I just said. And yeah, after the first article, then I got merged into upstream and will probably, the code will be part of PCP 532, expected end of July this month. Or, well, yeah, it's also in the current top of the tree, however you call it nowadays in the Git times. So much for the first of the two articles. Now, what can we do? Why is it that I was actually interested in this? Of course, to look at the values. So, what is it practically looking? We have anyway here a system. So, PM info Denki. Let me unplug actually the power from the system. I'm remotely logged in on host Guiderush here. I think ThinkPad 460S next to me. And I have now queried which metrics below the domain area Denki are available. What do we see here? Let's better first look at this here. These values here are what I was previously looking at directly with cat on the sys file system. So these are raw values. If I execute the same now again, we see that these raw values have increased a bit. Yeah, and here we see the pieces from the battery. So battery values are just coming. Well, the charge level of the battery we can see at all time, but battery now, for example, we just see active when we are living on battery. So what are our actual readings? I can get the output of this in a vmstat style format with a command like this. And then I get in 1 second time frames what's the system doing. But anyway, let's take 20 seconds. Why do we see NA here? That is because we have just started the client for querying these values. And as I said before, these are increasing counters. So what we're actually interested in is by what value, how much have they increased? And that computation is also, it's just possible, of course, with reading two values. With reading two values, we can compute the difference. So we know current package consumption is around 0.3 watt. If I could, I would probably cut off two digits here because, yeah, the 3 digits after the decimal point is just not reflecting the accuracy of what it is. But anyway, it's what I guess I get from REPL. What you are looking at here is the current charge level in raw from the battery. The system has a speciality, actually. It has two batteries, and I'm currently here just I'm just consuming from the first battery, but I see it's constantly going down. And if I would start something, if I would consume more, then it would be going down even faster. The energy now rate is what I'm consuming. I am in 60-second time frames. I'm looking at the current charge level. This here is 16 kilowatt hour, I think, yeah. And this here is actually once per second computed by, I think, firmware. And yeah, and we see also my 60-second values are diverging around what the firmware thinks in 1 second time frames. So yeah, in the article, I'm also having one of these outputs, and I'm describing this. So why is it that I'm not just going with this, but I'm providing the raw value here? What is this good for? One of the usages is, as I said, I have a software. I release a new version of the software. I want to see if the software consumes more power for the same task. Then I can run the software, and I can then measure to measure in the most efficient way how much energy the application was consuming. I should use basically the raw values here. I should use an application which is running long, maybe 5 minutes, maybe 30 minutes. And I should look at the start of the time frame, at the current charge level, and at the end. And I should use the difference to just know how much the energy or the whole system, I hope that the application is consuming most of this, was consuming. To say this a bit more with diagrams here on the left, we see if we would use power now to compute how much an application, for example, running for 5 minutes would consume. Basically, we are looking at the charge level of the battery. That's this graph here. It's the same on the right. And if we are looking at power now, we would be looking at this in 1 second time frames, at least 1 second time frames. Of course, we know power now is changing once per second. We would get this kind of stripes, and we would then count together how much power we were consuming. To the right, we just have 2 times actually T1. We are starting the application, to time 2. We are stopping it. And what we want to know is the consumed power, so this area below the graph. And this is exactly what we get in just looking at our charge level here, looking at our charge level here, and then doing a computation. So for this kind of a bit longer term measurement, you can get better accuracy if you look at energy now. So, and we set out of survey. What can we do? Give me something interesting. Yeah, I'm doing the internal calculation, as I said, in 60-second steps. If you run an application like 5 minutes, then you can do the computation manually, just looking at the charge level at the 2 times, and then compute this with 300 seconds or something. So we discovered 2 technologies, REPL, which tells us about CPU, DRAM, memory, and oval system. But we have so many more components. What can we find out about the consumption of single components? I was wondering. So I started, and I was designing the system to get down to as low energy consumption as I could get it with reasonable research, and that's what I came up with for this Intel system here, 1.3 watt. This is basically in just running, not running software you do not need, in running PowerTop minus Autotune, and I discovered TLP. TLP is quite cool. It has so many options. TLP Start is just doing like a basic setup, and it's very recommended. You should be aware of one thing. So one interesting, nice feature is before I mostly run my systems, also they are laptops, I'm running them with power plugged in. And then it's not good for the battery actually to be charged up to 100%. So in this configuration, by default, just keeping them at the 80% level is a good idea. This is what TLP is suggesting. And the second interesting thing it's doing, it has a battery optimization mode, it says. Basically just let me survive because I'm on battery longer, which is capping the CPUs. So it can also restrict CPUs to not clock higher than 1.6 gigahertz, for example. I'm just mentioning this because if you run benchmarks, then you will also get less computed, so less computation power after running TLP Start with default options. Anyway, trying to find out consumption of single devices. This is what I saw. Shall we start with the raw data? Let's start with the raw data. So basically, this is the output from more or less from PMDA Denki we were seeing before, and just under certain conditions. So this is a system in idling, and this line here is from my ThinkPad T460, and this line here is from my ThinkPad L480. And we see overall REPL is down to 0.3, 0.2 watt. This is the overall system consumption in idle with disabled screen down to 1.6, 1.4 watt for the ThinkPad T460. And with this, you can already do a simple computation because you can actually subtract what you see from REPL, and then you see that the rest of the system is using 1.1 watt. What's the rest of the system? So if we can trust our sensor from the internal battery, and if we can trust this sensor here from REPL, then the difference is these guys here. So our NVMe or SSD, our display, the display was disabled. The fan was not spinning. The internal bus, this unaccounted stuff is using up 104 watt and 104 watt for the ThinkPad L. Any guess what the S is? Yeah, I was in the past speaking about running Linux on the Nintendo Switch. So of course, this is an idling Nintendo Switch. Screen not completely run down, so nonetheless idling at 0.9. Numbers when running 4 times MD5 sum. The overall consumption of the systems is for the ThinkPad T 9 watt. We get 10 watt for the ThinkPad L480, and we get 4 watt for the Nintendo Switch. And we see also that, as expected, we hoped to see CPU to be the one under load, and RAPL is actually also showing that. So we see a bit more load on our memory when running MD5 sum on dev random, and we see much more load on our CPU cores. That's actually what we expected. And just a plain 4 for the Nintendo Switch, because I can nicely access the battery, so I can see the overall consumption on the Nintendo Switch, but there is no RAPL like we have for AMD and Intel. It seems like some ARM vendors have something on boards, but I didn't. Yeah, I have none of these around. Regarding ARM, I anyway have just a Raspberry Pi and the Nintendo Switch around. So trying to find out how much our gigabit chip, our Ethernet, is under full load consuming. So of course, to see what how much load, how much additional consumption we would cause with we would get from a certain component, I was putting the component under load. So receiving the maximum amount of data it could receive via Ethernet. We see that we get a bit of CPU load. Again, the top line here, this here is idling. So we get like 1.2 watt additional consumption on the CPUs by putting the network chip under load. And our overall system load, overall system consumption goes to 4.3 or 3.9 watt. So and with these two overall the consumption, and we know what the RAPL values all in all are consuming, we can then subtract. So we also know what the idle system was consuming, 1.4 watt. So if we from 3.9, if we subtract the CPU stuff, the RAPL value, and if we are subtracting what the rest of the system is consuming, then this would mean that our CPU, the additional consumption from our Ethernet chip is 1.2 watt on the ThinkPad T460 and 1.1 on the L480. Doing the same for sending gives us comparable values, 1.5 watt, 2 watt. Wireless network is not too far away, actually. So wireless chip is apparently consuming 1.4. Well, wireless chip plus the bus, so the data which we are receiving is also going over the bus, are apparently around 1.4 and 1.1 watt. The Nintendo Switch, by the way, did jump from idling 0.9 to 3 watt. Yeah, but I don't know what part of how much the CPU was taking, so I can also not guess on how much the wireless chip was consuming. wireless sending, wireless receiving. So what if we put our SSD or NVMe under load? The ThinkPad 460 has an SSD, and this looks like 3.3 watt consumption, more consumption by the SSD. And here NVMe under load for the other system, 2.7 watt. Nintendo Switch, well, 2.4 watt looks good, but well, we also have just no full-blown NVMe or something. This is just slower interfaces, so this is just an SD card slot. Yeah, it's also delivering lower performance. We have a further test for stressing our SSD, which is well, HDPAR minus T, and we see just 520 megabytes per second for the SSD in the first ThinkPad, and the second one has 4 gigabytes per second. And we see again for the NVMe here lower consumption than for the SSD. HDPAR is offering a second performance check, which is also giving very different results of SSD versus NVMe. This is apparently just transfers inside the device itself, 8 gigabytes per second versus 19 gigabytes per second. And yeah, performed on the Nintendo Switch, we get also 1.5 gigabyte per second. So, and lastly, here we have the internal screen. How much does my display actually use up? When I said idle before, I was basically starting a really simple X session with a simple window manager, and I was running XDMP set off, so just turning off my internal display. Now running the display with high brightness and computing, we see, wow, 4.2 watt for the ThinkPad, the first ThinkPad, second one, second ThinkPad, more like 5 watt, 1.2 watt for the Nintendo Switch. Yeah, I would love to see the Nintendo Switch, which was with the organic display, which was announced this week. But anyway, the newer models are locked down, so even when released in October, they are probably not directly loadable with Linux. Anyway, the second difference here for the Nintendo Switch is it's a touchscreen display. So already this functionality is taking up power. Yeah, and low brightness. So how much can we influence the overall runtime of the system, for example? Then with just lowering brightness considerably. We have down by more than half here for the first, and also even more here for the second ThinkPad. So pure numbers are boring. This is the screen. This is the diagram. To the left, we have the idle. Then we see how much power the overall system is consuming when putting SSDs, or well, for the Nintendo Switch, that's the SD card reader, under load. Ethernet load is comparable. Wireless network causes load consumption comparable to Ethernet. Then full steam access, full steam CAT of our SSD is actually causing quite some load. Display high, and most load is when putting the CPUs under load. We can also take out, so this is the overall system load. We can also subtract. So we now idle. We try to use as few power as possible. This is what I call idle. So then when putting Ethernet under load, I know what the system was using before. I can also actually subtract the idle consumption from this one here, and then I could say, looks like 2 watt consumed by Ethernet chip additionally when it runs on full steam. This is what I have been doing here. Consumption or additional consumption caused by the single components. Display high is consuming quite much, and I was taking out the CPU consumption here because, makes no sense. So much for software, for hardware. What can be found out about software? Again, 2 scenarios. One is you have a software with a workload, and then you release a new software, and will it not only run faster, but also will it consume more or less power? That's good to know. And the second one, I have a certain task I want to, and I have various softwares. I want to use the best software for the job. Let's start with the graphical data this time. Raw data also available. Idle without running X is here on the left, and that's the same idle we did see before. And then we have the screen with half brightness. We have here on the Nintendo Switch the task of playing an X264 codec encoded video with the totem player, which is also command line, but not horribly nicely optimized apparently. We have on the 2 sync pads playing the video with MPlayer, playing the same video with VLC. We see that on one of the sync pads, VLC is doing worse and consuming more power. We have here the same video playing on Google Chrome, which consumes more than on the standalone players. We see also that the Nintendo Switch does the same task with half of the power. We see playing of the video with Firefox needs a bit more power than on the sync pads. Needs also more power on the Nintendo Switch. Then something graphical. I will just show it in a minute. There's a nice WebGL demo of the game Wipeout, which I like. So 3D via browser, done via Firefox and via Chrome. And we see Chrome using up more power. And we see here the Nintendo Switch, the same task uses less than half of the power when done here with the ARM CPU on Chrome, on the Nintendo Switch. I should note, though, that the graph here is just looking at the consumption. I'm not looking at frame rates. I'm not looking at subjectively how smoothly is it running. So maybe on Chrome it's running with a higher frame rate and more smooth. And that's not factored in here. That here is just looking plainly at the power. What's this WebGL thing actually I'm talking about? Not sure how good or how bad this is coming up in the video stream, but it's some 3D rendered stuff. Wipeout on PlayStation 1 basically. A last graph. RAPL is not only providing us with the one full bucket for CPU plus GPU plus memory, we get more. So we can actually see if the GPU is utilized. Not for Edward, because the NVIDIA stuff is of course not on board. But for the integrated chip on the Intel chipset. So wipe out Chrome, or well, let's look at this differently. We have again our different tasks, and in the different colors we have the components, how much the single components are using up. From the bottom, I tried to minimize for these tests the idle consumption, of course, but I had to display the application somewhere. And if not over network, I had to run a display, of course, but with low brightness. That's what you see in violet here. And actually, compared with the overall system consumption, the display is not consuming very much here. 2 watts for the display. On top, we have other, which is, well, unaccounted stuff like bus, fans, if spinning, and things like this. The blue stuff is our RAM, not too much different, but a slight trend of wipe out Chrome, using the RAM more heavily. The orange stuff is the pure CPU, and on top we have GPU, so our graphical processor. And we see Chrome making heavy use of this. By the way, this all here is just from the ThinkPad T460, with one exception here. This one, Wipeout Firefox, is from the other ThinkPad. And comparing this with to the left side, the ThinkPad, the same test on the ThinkPad 460, we see also happy to see that there's not much difference. Yeah, just slightly more usage on consumption on the ThinkPad 460. So this was looking at what is my software actually using. So, and actually looking at this graph here, and considering that I'm just looking at the REPL values and the overall system, so the battery, having the other stuff computed and concluded, is not too bad at all, I think. One last thing, also for these, in case someone is interested, of course, raw numbers are also available. So one last thing. I did see all of these numbers. So REPL is telling me from this sensor, hey, I'm using 3 watts at the moment. But then I'm like, really? Can I trust you, guy? Can I trust you on this? You see this value reading, you see this sensor reading. How reliable is this? How could I measure this? I hate hardware in that I do not want to break up the ThinkPad for other things than upgrades. I don't want to stick in measurements. So how to measure something? Well, so these other consumers here, we have them actually pluggable. We have actually also USB here. And we can actually externally plug in USB consumers. And when we plug in a consumer, we can externally measure how much we are consuming. So turning this idea into reality, on the first ThinkPad, we have again idle consumption of, from this run, I was idling with 1.4, 1.5 watt. I did hook on my first consumer. And using the external Satoshi meter, it told me consumption 4.4 volt, 1.4 ampere. So this makes 6.1 watt consumption measured externally. And I did see that internally our REPL values are stable. That's great. That's confirming that our CPU is not involved at all when we are connecting a USB stuff. And we see that our internal battery is discharged quicker. Good. That's what we expected. So taking off, subtracting from this here, so our idle load, let's assume our idle load is also with the external consumer as it was before, 1.5 volt. We can then nicely compute that. Apparently, for our internal battery, our additional consumption is 7.4 watt. Or we are now discharged 7.4 watt quicker than before. And our external device was telling us 6.1 watt, which is not too bad. Second consumer, 2.4 watt internally measured versus 2.4 watt. And then with the different ThinkPad, we see I did use a different cable actually. So I was able to provide 2.8 ampere. So this was whooping 16.8 watt discharge internally, all in all, minus our idle load. Additionally, for the USB consumer, 15 watt, and the external device was reading 12.8 watt. Second consumer, 5.1 watt versus 4.4. So not too far off, and interestingly, always off in the same way. Did I write it down? Yeah, actually, these values are always off 14 to 20%. So actually, I have no idea about system design, but maybe the conversion from the system battery to what we provide to the USB port is just taking up something like loss or when transforming. No idea. So, and that's all I had for today. Any questions and comments? If you have any nice ideas on what one could compute or what would be interesting to know, that might also be interesting to set up future projects for what to measure.
I'd kind of be interested to see what a machine learning task could take up, or whether it would CPU load and those sort of things would be going up, or something like really heavy on the GPU side.
Or when you make the mistake of needing swap.
Yeah, I think I see the comparison for various CUDA jobs, or I see this comparison mostly people looking at the runtime and they say I have this new model and I'm comparing the runtime on the same hardware, but yeah, right. So there is something for NVIDIA at least. I did also research other energy consumption measurement projects. I mentioned it in the first, and there is LibAviorum, and they have also an implementation for NVIDIA CPUs. It's not open. Well, the implementation is open, but of course you need proprietary libraries apparently. So they are for abstracting this kind of reading. I did just implement directly in C what I could use on my hardware, the battery stuff, the REPL stuff. They have in this library abstracted REPL. This is what they do here. This is what they mean with platform Intel. They have something from Intel, from IBM. They have from NVIDIA, what I said, they use the GPU. They get an idea about GPU consumption, but they have to use, here. Volta is the generations they support, and they use the CUDA toolkit. So to the least, external stuff has to be installed. They also have something from ARM, but very specific. To my understanding, there's nothing as generic as REPL for ARM. That would have been very, very cool to show next to the Intel values. I think this activity here is also, so my ideas were like personal interest and this scenario, I'm on a train, I'm on a plane, I want to do a task with the best software. But the bigger idea is also, I hope that open source projects get into the habit of doing test cases with their new versions of software and giving them minor testing, at least, of energy consumption. I know there's a project for the Linux kernel, which is aimed at compiling new versions and aiming at they're running test loads, but just looking at slowdowns of some common compute tasks. But with climate crisis and things, I suspect that interest in optimizing for energy consumption might also be something getting more interest in the future.
So having done some of this measurement, have you actually changed how you use your laptop? Have you, do you throttle the CPU more often or intentionally, or have you become more conscious of how bright you have the screen, or has this changed your habits anyway?
Yeah. Instinctively, actually, I was doing, how should I say? Before going to KDE, I was on a on a more optimized window maker actually for 10 years. So regarding software, I have moved to a heavier beast recently, or 1.5 years ago. But for software, for example, for playing videos, for example, I use MPlayer since ages already, and MPlayer has also here from my testing turned out as being the most efficient stuff on the architectures I looked at. So maybe it's my purism, or my purism is in line with, or my trying to do things simple worked out also energy-wise. But the tasks I looked at, actually, I'm already doing optimized. Along with this, I was getting, so for optimization, I was using PowerTop minus, what is it, AutoTune already as part of my startup scripts, but I discovered TLP, and I will definitely look deeper into TLP for optimizing. That will be a good thing. And one thing I can also consider is, for example, online conferences, video chats, which seem to suck up 100%, no, 70% of your CPU, independent of what you do or which kind of CPU you have. So I consider actually to do capping on for these tasks, to just limit my CPUs to 1.6 gigahertz or something. Maybe the video resolution will go down a bit or something, but this kind of optimization is also possible. Yeah.
I'd kind of be interested to see what, if you're just doing like a fixed compute, what the effective frequency and total power consumption is. I mean, I would expect maybe if you increase the frequency, it's going to go up, but what sort of, how that actually panned out. So, yeah, for example, you're doing a compute that might take, 20 minutes or something like that, what the power difference would be depending on the frequency. If you capped it. Just, your assumption is, I guess, that, as the frequency goes up, maybe it's going to decrease in efficiency but increase in actual performance. But I'd kind of be interested to see whether that is a big case and whether to what extent that is the case. I'm sort of interested in from a server perspective more than from a laptop perspective. But for example, if you've got a cluster, are you better off running, something distributed at low speed on a whole bunch of nodes, or are you better off at, or if it's not time sensitive, are you just better off having it running on a node that's, CPU's running slower, or on, a single thing and have it running much faster? At what point the performance or the power is actually increased, the total power consumption, be kind of interesting.
Yeah, right. Or in other words, for example, if you have a set workload like compute P for the first million of digits, then that's a nicely frameable set workload. You could perform it on a ThinkPad with an Intel CPU, and it could take 5 minutes with consuming all CPUs and maximum frequency. And then if you cap the frequency at half, will it take double the time or maybe just plus 20% and use up all in all just 70% of the power or something, right? Yeah. So for this graph, so the how much computation is done, it's not, for example, here in this graph, right? This would be, it's quite specific to the task one would, of course, want to do.
Well, it'd be an interesting dimension to look at tasks that, not just necessarily cost, but also, the power dimension. What different approaches could give you different power, what sort of power usages. But I mean, I guess you'd assume with Bitcoin and things where they're doing all this stuff on GPU that it must be more power efficient to do it that way. Or is it more time efficient and they're looking at the total cost of ownership of the hardware?
The investment initially in the hardware is just the smallest part of that. The power is the most interesting in that equation for these guys. And because of this, we did see the extreme shortage of GPU cards, because the initial invest, it was not really important, but how many hashes you could get out of the hardware per electrical power you are putting in. Right. That's an interesting dimension, actually. Yeah.
Well, in that case, you would assume then that just running it on faster hardware is actually more more power efficient. But I wondered, does that translate to hardware running at a higher frequency, or the same hardware running at a higher frequency being more efficient? So is the hardware more efficient, or is the fact that it's running at a higher frequency making it more efficient? And then I guess if you could overclock, you could also look at whether whether there is a significant increase in the efficiency running it.
I would guess that these current miners, I would not think they are at 4 gigahertz or something. I would think I know they are cooling with, or when you see these farm pictures, then these pictures of farms, then these look hundreds of gigahertz, or they are mostly actually cooled with air, as it looks like. So those are not gigahertz, but these ASICs, they are also optimized just for exactly this one task. But yeah, and the measurements are probably hashes versus consumed energy, and size of the die or investment in the beginning is probably not that important. But it's the same area of interest, of twist actually. It's consumption versus how much you get computed in a certain time, and yeah, right. It's the same twist.
Yeah. Well, it'd be interesting because I imagine if you're overclocking something too much, you'd start getting maybe increases in heat, and that sort of thing might, or like the increase in heat might actually make it less efficient per watt. But
I'm thinking, my guess would be that the increased voltages would result in more energy loss to heat, because don't you normally need to increase the voltage?
So if you under voltage it, you might actually make it might be more efficient.
That's my guess, because I mean you'll get more heat anyway. I mean, just running the clock faster will result in more heat, just strictly because the clock is faster, but you're also getting more work done.
The thing is there more heat per work, or is there like, what point does the heat and the work balance out?
I'd be curious to hear that too, but my guess would be that the higher voltages would result in lower or more power usage, proportionally more power usage, and I think the higher voltages are usually necessary to overclock or higher clock speeds.
Well, it's the error rate you get. Once you get too low voltage, you start getting high error rates because it can't detect the difference between a 0 and a 1.
Sure, right. Well, I mean, yeah, the same thing happens if the voltage is too high too. But So yeah, you've got to. You're right. You can't just keep cranking the voltage down forever. At some point, you're right. It's not going to work properly.
Well, I just remember, like I had low power memory in one of my machines, and the big difference was the voltage it was running at.
Right. But then they're also, because the voltage is lower, they're probably limited to lower speeds as well, right?
Well, I think the difference was it was just higher spec memory. So it was more expensive because it was higher spec, so it could handle the lower voltage without having errors.
I see. Yeah, that could be too. I know some of the memory chips I've used just to get the higher speeds do require higher voltages. Like some of the memory will run in either low power or regular power mode, but in low power mode, the clock speeds are limited.
So anyway, sir.
But yeah, that would be an interesting test.
Well, I'd also be interested to see things like, just with ARM CPUs. I mean, I think a lot of really cool stuff have been done. I think Apple's been doing some pretty cool stuff with, some of the ARM CPUs they've got. But I'd be interested to know whether it is just really using the software or combining software really well with the hardware, or whether it's actually that the hardware is offering better performance.
I'll bet it's both, because they're selling billions of those or whatever, or millions, and so they've got them extremely optimized. I mean, it's all the software and hardware is all going to be extremely optimized for that specific task.
Yeah, well, considering the fact that Fujitsu has, for example, in the Fugaku also constructed HPE aimed CPUs with on ARM base. Also considering, well, no details of course, but considering that in the Linux world, so many people are waiting for Linux to become available on M1 architecture. We actually have even Hector Martin is actually living in Tokyo, the main head behind SRE Linux for porting Linux kernel to CM1 architecture, and I think we have many people in agreement that they like what they see, what they know so far about the hardware, and they are optimistic on being able to make good use of this with open source software like Linux, and it's not so proprietary that it would only be usable from macOS or something.
That's good. So they're getting like support or documentation or whatever, one way or another, they're able to get all the details they need for it.
A part is open because it's ARM,
Right.
but then this is like a sketchbook, and then every vendor is doing their own implementation, and yeah, so there's like a diff which has to be found out, and this is what the project Hector is about, to find out what is required. At this point, I think the basic kernel is running, and now he is researching actually a minimal task switcher. So like for development, now being able to, like the Xen kernel was also had the idea of running below the Linux kernel and then being able to switch tasks on top. So what Hector has planned and is implementing right now is also to have like a minimal task switcher on top of the hardware, which can then switch between Linux and between macOS, for example. It's not required in the end to run Linux on the M1 with this virtualizer in between, but it's good for debugging things, for starting on top. Yep.
It sort of sounds like really they're just reverse engineering. They're not getting help on it, but if they're trying to run both of them at the same time, so they can see what the actual hardware is or what the actual operating system's doing.
I guess there is no big business case for Apple to get Linux on this, but at least they are also not looking at a way like the Nintendo Switch, for example, is locked down from Linux or something by default. They have set up so you could run your own userland, your own kernels by default. They are not artificially putting big things in the way of people, at least.
Right. I don't know. Yeah, it'd be nice if Apple had more of a developer focus, because a lot of developers are going to want to use their systems with Linux. But yeah, that's going to be an uphill battle if they're reverse engineering it. I mean, like you said, ARM is pretty standard, which helps, but still there's going to be a lot. If you want to use all the accelerators and stuff on the chip, that's going to be a lot of work to reverse engineer that if that's the route they have to go.
My impression of what I was hearing was it was more like an embedded system where each system's going to be custom. So it's not like, you have a standard bootloader, like on an i86 kind of machine. So if that's the case, then presumably it's going to be different for each piece of hardware that they're going to do, and it's going to be a real pain to actually get it all working and keep it working. And then there's something also to stop Apple kind of having the same product but having it using different hardware.
Yeah, that'll be a pain. Although I imagine they'd want to reuse as much of their bootloaders and stuff as possible.
Yeah, maybe, but I guess if they're selling it as a consumer product, then it's kind of, if they work out, for example, how to make cheaper hardware, or to work out how to or for example to handle large supply chain issues or that sort of thing, they might switch out stuff, and so ostensibly you're buying the same product, but it might actually have different hardware.
Well, that's true. I mean, yeah, they may not, they may switch out the hardware, and maybe they won't update, like ACPI tables or whatever they use, or to identify what that hardware is. It might make it harder for, third-party developers. But
I'd just be really interested if it sort of prompts a bit more server-based ARM stuff. I mean, the Amazon sort of ARM-based stuff is kind of interesting, but obviously that's purely for them. So, but it, you could start buying ARM servers, with decent CPUs and that sort of thing in them.
There's got to be something like that out there now, isn't there? Or is it all just custom stuff that AWS does?
Well, it seems like you've got supercomputers, you've got Apple machines, and you've got Amazon making their own kind of internal stuff. I've seen some sort of 64-bit development boards, but not really. Well, definitely not what you would call a server. Just sort of stuff with basically for system on chip kind of stuff.
Oh, interesting.
But then I guess you could have something more like the modular computers where you just basically buy a bunch of compute and then whack it into something that hooks it up with hardware.
Yeah, it seems like I heard of something like that or read something like that. I'm kind of curious.
Yeah, I guess currently people wanting to play with the architecture. Well, yeah, for servers there are 3 or 4 big boards out, but it's not really like something would really get a big head off or something. I mean, for example, the Fugaku hardware is, for example, supported by Red Hat Enterprise Linux. But for the other vendors, I couldn't name one right from the top of my head. People playing use, for example, Raspberry 4, which is ARch compatible and runs Fedora or something. But yeah, it's of course not what you would call enterprise ready.
It seems, there's potential for it, except that you can only use it on the cloud or,
I just Googled ARM server just for the heck of it, and it looks like Gigabyte is making them.
Wasn't there recently also some big buy-off? High Five was bought or something?
Is that ARM?
In the ARM world.
I'm not sure they were bought, but they're doing a joint venture with Intel. Intel's going to do their next generation.
So Intel has given in.
Yeah, Ampere. Oh, so sounds like they can be had if you want one. I don't know.
Okay, I wonder what. Okay, it's 64-bit, yeah.
Please excuse me. I've got to go deal with the carpenters again. But thank you very much, Christian. That was quite good. I was very interested in your presentation, and I had no idea about how that sort of granularity was already available inside the machine. So thanks.
Thanks, good to hear.
Goodbye, everyone. Sorry, I've got to run.
See you, Jim.
See you, Jim. I might just stop the streaming.
Okay, yeah, I guess we're doing for now.
Unless someone's wanting to say something really insightful, and we need to keep on the.
I'm waiting for you to stop the streaming, then I'm going to say it all. Put it under wraps.
Let's see. Oh, okay, no, I didn't stop.